Okay, so for today we have chapter 28. Let's solve some problems on interference and diffraction. Problem number one, we got two students sitting in the room listening to two loudspeakers and they are in phase. So the given conditions is in phase. And it's also given that we can hear a maximum sound. Maximum is clearly the key word for constructive interference. And the question is, what's the possible frequency of the loudspeakers? All the geometry parameters are given. We got the parameters for the room and the position of students. So let's see what we have for the first student, student A. So looking at the geometry of the case, we can see that the distance to the speaker on the left and the speaker on the right, it's the same distance. And this is your condition for student A to hear the constructive interference for this scenario. Now for student B, you can see that the student is not the same distance, so we have to consider constructive interference case when the difference between path lengths is a multiple of lambda. Lambda is the wavelength, and using the given condition, let's solve for the geometry for student B. So the difference between the path lengths is the multiple of lambda. And take a look at the Pythagorean theorem here. You got a right triangle. L2 is the hypotenuse, and S and L1 are the sides of the right triangle. So side squared plus side squared is the hypotenuse squared. Here we go. Solving for the hypotenuse, you get the distance to the loudspeaker on the left. And if it's the maximum, your M, so for the first, like as one of the options, M can be 1, and L sub 2 is what we just found here. L sub 1 is given as what? As 1.5 meters. So the difference between L sub 2 and L sub 1 is the difference between those two numbers. So we're getting this number as 1.854 meters. Considering sig figs, don't forget that we need an extra sig fig for accuracy. It's not the final result. Remember, we're looking for frequency, not the wavelength. So I'm keeping one extra significant figure so that error does not propagate. So this is the wavelength. It's the option for m equals to 1. You can also get the same for m equals 2, m equals 3, but it's not going to be the most value, the maximum value. And you have the frequency formula. Frequency is always some kind of a speed divided by the wavelength. Remember, it also works for light. It's not just sound that has this connection. For an electromagnetic wave traveling at the speed of light, you have the same connection. Frequency is the speed divided by the lambda. And if it's the sound, it's 343 meters per second. It was not given specifically, but every time we're talking about the speed of sound, it's the default number. It's like the default number for the speed of light when it's 3 times 10 to the power of 8 meters per second. And the lambda that we just found from the difference between the path lengths. Once again, it's the constructive interference condition that we use to get to take care of the word maximum in the given conditions. So frequency of 185 hertz, 3 sig figs. It's not 4 sig figs anymore, it's 3 sig figs. Hertz is your System International Unit for frequency. Uh, that's it for the first problem. Now another problem, similar setup, but now the given condition is that it's out of phase. So it was in phase for the first problem. Now it's out of phase, and we are looking for uh, minimum or maximum for 3 students. Now we have Curly, Larry, and Mo. So the first question is, what's going on with Larry? Is that a maximum or a minimum that the student registers standing at this point of the room? So the keyword is out of phase. That means that one signal is at its peak and the other one is at its trough. So those are the keywords for maximum and minimum. So peak is the maximum, trough is the minimum. And here is a diagram from the book that shows you how the two waves interfere with being out of phase, the 180 degrees, if you will. This is your phase difference. Sometimes you will hear the word phase difference instead of out of phase. Those are the same statements. So part A, we got the Larry, and you can see that Larry is once again standing right in front of the loudspeakers, and the distances are the same, but the loudspeakers are out of phase, and because of the out of phase given conditions, Larry will hear destructive interference, and that is your extra lambda over 2 component added to the distance that is traveled by the first wave. So first wave travels whatever distance L1, then the second wave must be traveling the same amount that the first one travels plus the lambda over 2 to make it out of phase. And now the second question is for the lowest frequencies that produce a maximum sound. So for maximum sound, that's constructive interference for Mo and Curly. So let's take a look at what Mo experiences. Well, yeah, he's going to experience the constructive interference, but let's take a look at the geometry for Mo. So what do we see? We see the same L sub 1 and L sub 2. And for maximum, in order to get the maximum, the constructive interference from something that is out of phase, you have to start with the out of phase, to see the in parentheses expression that we used for Larry with the same logic. And it's another lambda over 2 to make up for constructive interference rather than destructive interference. So if Larry had the destructive interference and now we want the maximum for Mo and Carly, we need to add another half of the wavelength so that you do get the maximum. Without this lambda over 2, outside of paren, you will still get the minimum. So plus lambda over 2, and we get the maximum for Mo. So the difference between the two path lengths is the lambda over 2. And if you want the second lowest frequency, you have to add another lambda. If it's the third lowest frequency, that would be 2 times the lambda, and so on. So that's the logic for those coefficients m that we have. So distance-wise, geometry-wise, Mo is 3 meters away horizontally, and then see how it is a little tricky with the vertical distance. The total distance is 1 meter and 1 meter for the room, so 2 meters total, and the loudspeakers are 0.8 meters in between. So how do you figure out this distance? Well, if they are equidistant from the walls, then you have The total is 2. Take away 0.8 for the distance between the speakers and cut it in half because we have 2 of those pieces that we have to add up. So 2 take away 0.8, it's 1.2. Divide by 2, that's 0.6. So this is how you find the vertical distance for Mo and Curly. For Curly, by the way, it's going to be the same 0.6 meters between the wall and the loudspeaker. And once again, the right triangle, so 0.6 squared plus 3 squared gives you the hypotenuse squared. So you get the distance between the loudspeaker and the Mo. And following the conditions that the distance between L sub 2 and L sub 1 is lambda over 2, you solve for, where is it? Yeah, right here. So set the difference to half wavelength, and the first maximum is whatever that is, it's 0.502 meters. And for the frequency, it's your connection between the speed of sound and the particular wavelength. That gives you 683 hertz. For L sub 2, it's another right triangle. You can see that we got 0.6 and 0.8 to consider, and this distance also goes squared. The other side of the triangle is 3 meters that is given in the diagram. So solving for the hypotenuse, we get the second distance traveled by sound from the other loudspeaker. So once again, the trick is to read the given. If it's out of phase, then you have an extra lambda over 2 to begin with. And if it's just by itself, then it's going to be destructive interference. And for maximum, for constructive interference, don't forget to add another lambda over 2 to make up for the extra distance traveled by sound, so that you do get the constructive interference instead. Okay, next problem is now laser. So laser, that's light, right? So laser light, it's light, so there's no sound anymore, but once again, it doesn't matter if it's electromagnetic waves or sound waves, you still have the interference and diffraction registered, and we have to solve for what? A pair of slits. This time it's a double slit. And the question is about the slit separation, so that you get the first order maxima at angles of plus minus 25 degrees from the incident direction. So let's draw a sketch and see what we have given, what's missing. This is your standard diagram to refer to. You can see the central maxima, the m equals to 0, and it's the 0 difference between path lengths. The slit separation is what we're looking for, so d is unknown. And for bright fringes, the maxima, we have the condition from the textbook, the d sine theta equals m lambda. The proof for this equation is in the notes and in the textbook. We're just going to use the formula by itself and solve this time for d. D is unknown, so we'll try to solve for d. The first bright fringe means m is 1, so plug in 1. The wavelength is given. Be careful, it's nanometers. Nano is 10 to the negative 9th. So have to convert that to meters. And the angle is 25 degrees, so sine of 25 degrees. Make sure your calculators are in degrees mode, not radians mode when doing the calculations, and you should be getting 1.6, and it's micrometers. Once again, please don't give me prefixes on your papers. I want to see scientific notation. So 10 to the negative sixth for the micro, and 10 to the negative ninth for the nano. Next problem, once again, double slit. The screen is 1 meter away, and it's now the third order, and it's minima now. See, it was maxima in the previous problem. Now it's the minima, and it's 22 centimeters apart. What's the width of the central bright fringe? So once again, the diagram, we definitely need the diagram. What's given is the distance between the slits and the screen, so 1 meter, and the width between the, what is it? See how the end of the second bright fringe is the beginning of the third dark fringe. And this distance is given as 22 centimeters. Make sure you convert everything into meters on the system international units as usual. So we're once again trying to solve for the distance between the slits. So using the small angle approximation, remember that those angles, the tangent of that angle has pretty much the same value as the sine of that angle, and the angle by itself in radians. So using the small angle approximation, and why is it a small angle? Because the distance between the screen and the slit is much larger than everything that you see on the screen. Like that 1 meter will beat any distance on the screen. And indeed, you can see we solve for tangent of that angle. This is your vertical displacement. This is horizontal. So the ratio of the components is the tangent. Solving for the angle itself, it's the arctangent. And it's the ratio between the two. That gives you 6 degrees. So it's indeed a small angle. Just confirms our small angle approximation condition. Once you figure out the angle, it's easy to work out any fringe. It can be number 1, number 2, number 3, doesn't really matter. For what we have here is the third order minima, and we want the central bright fringe. So third order, so m is 3. Delta L is therefore 5/2 of the lambda, so it's lambda over 2 for the first one, 3 lambda over 2 for the second one. So for the third one, it's going to be 5 lambda over 2. And this is the condition for dark fringes, for the minima. Once again, the derivation is in the notes, is in the textbook. We're just going to use the formula by itself. And we want to solve for D, but the problem is we still don't have the lambda. The lambda is not given. If you'll take a look, we only have the geometry for the slit versus the screen, and that's pretty much it. So we have one equation with 2 unknowns, and clearly you can't solve it by itself. So here comes the trick, which is, pretty common in physics. If something's not given, you can just make it 1 and see what's going to happen. Or the other trick is that we don't really need the d by itself. You can use the ratio. So if you divide both sides by d, you can see that it's now the ratio of 2 things that are not given. But it's the same ratio for the first order minimum as well. So it doesn't matter if it's first order, second order, or third order, the ratio of the wavelength to the to the width of a slit is the same. So using the angle that we just figured out, we have the sine of that angle with respect to whatever the fringe take away 1/2. That's the condition for dark fringe. And if m is 3, then subtract 1/2, you're going to get 2.5. And this is the ratio that gives you the ratio for lambda versus the d. And now for the first order minimum, it's the same formula. See how the formula is the same, but m is now 1, not 3. And the angle that we are looking for will have a different coefficient. 0.5, it's not 2.5, but it's the same ratio for uh, wavelength versus the width of a slit. So we don't know the width of a slit. We don't know the lambda, but we don't need to solve for any of that. The question was for the angle, and using the ratio that we figured out from the previous analysis, we get to the angle anyways. So it's a little tricky in terms of algebra, and you would say, hey, there's just not enough information given. Every time you bump into such a condition, try to look for those two tricks. The first trick is just to make something equal to 1. And the second trick is to solve not for a certain value, but rather for a ratio of values. I mean, unknown values. And don't forget that if it's minima, then the formula is different for what you have compared to maximum. So you do have the extra lambda over 2, and you don't have any lambda over 2 for conditions for bright fringes. Okay, and oh yeah, and then the last step is to actually find the distance to the first minimum. Well, if you know the angle and you know the side, then you can solve for any other side of a triangle. This time, if the side is what we are given and we want another side, not the hypotenuse, then clearly the function is a tangent. So solving for vertical distance, it's the horizontal distance times the tangent of the angle that we just figured out from the previous part. So 1 meter times the tangent of this 1.253 degrees gives you 2 centimeters. And once again, I just want to stress that 2 centimeters is much less than the distance between the slit and the screen. That's why the small angle approximation is valid, and you can definitely use it to your advantage to simplify your calculations. If you want the entire width of the central maximum, then it's going to be the same value times 2, because with respect to the central axis, you have the same distance away. It's theta, say upward, and theta downward. You get like double theta, if you will, and double distance of what we just found from the previous step. So if it's 2 centimeters from the central axis to the first bright fringe edge, then for the bottom part of this fringe, you just add the same value. Okay, this one is another cool problem. We got green light passing through a pair of double slits, and you have the interference pattern shown. Now the question is, what is the wavelength of the second color? Is it longer or shorter than 505? And what's the wavelength of the second color? So let's take a closer look at the interference pattern. And starting from the first bright fringe, the central maximum, you can see that the green light is a little ahead of the other light. So there is a uh, special condition that is just given that the what is it, one, two, three, four, fifth maxima of the second light is actually one, two, three, four, five, right in the middle between number four and the five maxima of the green light. So if it's right in the middle, that means that it's going to be a minimum for the green light. So minimum for the green is maximum for the unknown light, and that's what we're going to use to solve for the unknown color. Oh yeah, this is another diagram that even has a better explanation. So maximum, minimum, maximum, minimum, maximum, minimum, maximum, minimum, maximum, minimum. And in here, all the maxima are shown. So you can see that fifth maximum for the unknown light is the fifth minimum for the green light. And that's exactly what we're going to use for the formula. Angle for the fifth order minimum is equal to the fifth order maximum. And it's the d sine theta that is your 5 lambda for the maximum. Remember, that's the condition for the maximum. Let's go back to the previous problem. So d sine theta is m lambda. That's the condition we're using for maximum. D sine theta is m, and m is 5 of the unknown lambda. That's what we have for maximum here. And for minimum number 5, here we go. D sine theta is m take away 1/2 lambda. So m is 5, take away 1/2. And it's not just any lambda, it's lambda for the green color. We know that it's green, it's given. So we set them equal to each other. So d sine theta is 5 take away half of the green wavelength. And you just solve it for the unknown lambda, and that's it. So unknown lambda turns out to be what? Once again, be careful with nanometers. You got nanometers, so convert that to meters. So 505 10 to the negative ninth of a meter, and you divide both sides by 5. And you get the 455 nanometers, and that corresponds to somewhat blue, maybe a little light blue color. That is the unknown color. So your unknown color is blue. So using the interference pattern, you can really answer all the questions about what kind of light that is, what's the wavelength, what's the frequency. We solved for frequencies before. Now it's just the wavelength. And once again, two conditions, one for the bright fringes, one for the dark fringes, and just look closely at what's given for number, if for what kind of number of the minimum or maximum that is. Don't forget we start from 0. It's another common mistake. People start counting 1, 2, 3, 4, 5, when in fact it is actually 0. 1, 2, 3, 4, 5. I guess that's it for this problem. Yeah, next one. We got a naval engineer testing a non-reflective coating for submarines, and that's going to help them avoid detection by producing destructive interference. So the keyword is destructive interference. The sonar waves have a certain frequency given, and they travel at a certain speed. See how it's faster than sound, but less than light. Once again, it doesn't really matter what kind of a source of a wave you have. They all undergo interference and diffraction. And the formulas are still the same. Well, this time it's reflection, and the phase change is because we have this reflection. The First phase change is when you get from matter with lower index of refraction to higher index of refraction. See if we have one for the A. One, two, one, two. Yeah, sorry, the headset turned off again, as usual. So we have the phase change between the two uh, matters. You go from lower index of refraction to higher index of refraction, and you get the first phase change from that. And then uh, from the reflective coating towards the submarine itself, you can see that for metals, you have like infinitely large coefficient of refraction. It's pretty much just reflected back into water. So two phase changes, two different transitions between two matters, and you have two phase changes. And t is the distance that the wave has to travel through the reflective coating and produce destructive interference between two rays, ray 1 and ray 2, must be going through destructive interference. This way, the submarine stays undetected. So, with two phase changes, each phase change gives you half for your coefficient analysis. And for wavelengths, we need the, once again, connection between the speed of your wave and the frequency. The speed and the frequency are both given. So we get a certain wavelength of 2.89 meters this time. And once again, the rule is for every phase change, you get half of a wavelength to produce the destructive interference. And then the phase change here is the another one half due to reflection. So combine those one halves together to get the final formula. So reflection plus, so reflection one half, and the distance traveled through the anti-reflective coating. That's what we get. And then it's one half for the second ray. I mean, that was the second ray. And the first ray is just one half phase change between the first and the second matter. So this is ray 2, this is ray 1, and the difference between them two must be one half for the destructive interference. So once again, ray 2 undergoes phase change here, and the t plus t, so you got one half for the phase change and one half for the phase change between the submarine and reflective coating, plus t traveled through and plus t traveled through. That's the first part. And for ray number 1, the ray in blue, you only have one phase change because you're going from air to the anti-reflective coating, and you get just one half. And don't forget that it's the destructive interference. So this is one half for the destructive interference. So the difference between the two rays is equal to one half. And you have to solve for, what is it, the t, the distance traveled through the reflective coating. Yeah, it might sound a little complicated here, but just follow the colors. The purple colors are for the second ray, the blue colors are for the first ray, and the red color is your destructive interference. Should make sense. Solving for t, that's just algebra. So one half plus one half minus one half is just one half. You got 1/2 and the 2 cross multiplication, or any other way you want to solve this little expression, gives you the 5 and 0.35 centimeters. Once again, I don't want centimeters. I want to see scientific notation. So for centimeters, it's 10 to the negative second. And that's pretty much it. So every time you go from a lower index of refraction towards a higher index of refraction, there is a phase change, and you have to add 1/2. Every time you're traveling through a certain material, that's the formula to do the calculations. Be careful, it's 2t. Why is it 2t? Because you're traveling all the way through downward and then you go back upward, so it's t plus a t. What else? Yeah, every time there is a frequency and a certain speed given, you can always solve for the wavelength. And that's pretty much it. Yeah, those are all the comments. Moving on to the next one. Oh, okay, this one is different. This one is a single slit. So the slits before were double slits. Now this one is a single slit, and we got 610 nanometer light. So we're talking about the speed of light, not sound or any kind of sonar. And now there is a diffraction pattern 2.3 meters away. Okay, linear distance is given. What's the width of the slit? It really doesn't matter what is given, what is missing. Chances are that we're going to use the conditions uh, uh, for the fringes, dark or bright. Uh, and for the condition that we are talking about, you don't have the angle. So we only have the geometry, but not the angle, which is not a big deal. We can figure out the angle from, once again, the small angle approximation. Your sine of a certain angle has the same value as the tangent of the certain angle and the angle by itself in radians. So let's take a look. We have the side of a triangle. We have the difference in the vertical distances being given. That's 12 centimeters. So solving for the missing parameter, the delta y is L tangent theta 2 take away tangent theta 1. You get the uh, missing angle. So instead of a tangent, I'm just going to go with the angle by itself. And once again, it only works for small angles. For small angles, that would be up to, say, 10 degrees, 15 degrees at most. After 15 degrees, you'll get a percent discrepancy that's going to be like, say, more than 10%, and that might actually affect the outcome. So this time, the distance between the slit and the screen is 2.3 meters, which is much, much larger than what you have for the screen distances. That's why it's the small angle approximation that you can use. So delta y is given, L is given. You can solve for theta just by itself, even though it's tangents that we are talking about. So with the knowledge of theta, you can get the sine of theta handy. And for any kind of a multiple, 1, 2, 3, 4, 5 for the m, you can solve for the width of the slit that we are looking for. So using the small angle approximation, solving for the width of a slit, capital L is given, lambda is given, it's 610 nanometers. Be careful with nanometers, convert to meters, like so. And divide by the delta y, because algebra says so. The answer is 12 micrometers. I don't want to see micro as your final answer. It's scientific notation that I'm looking for. It's 10 to the negative 6th of a meter. Okay, next problem. We got a Hubble Space Telescope. Yeah, it's not really working anymore. We got the Webb telescope that replaced the Hubble Space Telescope nowadays. Well, the textbook is a little outdated, so let's discuss the Hubble Space Telescope. So it was orbiting the Earth at a certain altitude of 613 kilometers. Be careful, kilometers convert to meters. And it has an objective mirror that is 2.4 meters in diameter, which is quite a mirror. It's like 9 feet diameter mirror. That's quite a mirror to work with. If you'll take an astronomy class, you'll understand that the bigger the better, and uh, it's going to give you much better resolution. And that's what we're going to discuss in this problem. So, if the Hubble Space Telescope were to look down on Earth's surface rather than at the stars, what would be the separation, the minimum separation of two objects, say two smiley faces, on the Earth's surface that could be resolved using 550 nanometer light? 550 is just a, just random number. You can use any other color pattern. Those wavelengths that you see here are just, colors of light that we collect with our own eyes. So for the minimum angular resolution, there is a Rayleigh criterion. That's the formula. Uh, don't ask me why it's 1.22. It's like a long analysis from many different experiments. The moral of the story is there is 1.22 coefficient, and there is a ratio between a wavelength and the opening for like what we call aperture. Well, when you're going to use parameters of taking pictures, it's going to be your size of the mirror that is given. So the two smiley faces that we want to resolve using that particular mirror, that particular optical device is L distance away, and that L is actually given at 613 kilometers. So L is given. The angle is what we're looking for. Lambda is, for example, 550. Once again, for lambda, it can be any other color. And we have to consider the small angle approximation as usual, because 600 kilometers, it's like 600,000 meters. So that's a crazy number compared to pretty much anything that you can talk about on the surface of Earth. The Earth by itself, just the radius of Earth is only what, 6,000 kilometers. So there's 600 kilometers above. That's going to definitely beat any distance on the surface. So small angle approximation is appropriate. The L is given, and Y is what we're looking for. So L tangent theta. This is just the trigonometry part, solving for vertical distance if a certain angle and horizontal distance are given. So L is given, and the Rayleigh criterion is pretty much given. This is the size of the mirror. This is the wavelength of light, and 1.22 coefficient to work with. So it is 1.7 and 10 to the negative first meters. So that's what it's like 1.7. Okay, we got. So it's still does not allow. Yeah, see, there's a note just to give you an idea. It will not allow you to read newspaper from space. It's going to be blurry if you want to read a newspaper on the surface of Earth from outer space, you need something better than the Hubble Space Telescope. You will not be able to resolve letters because it's a little less of a resolution that we obtain. For your understanding, it's still much better than a naked eye. The angular resolution for Hubble Space Telescope was about 10,000 times better than what you have in terms of your own eyes. So it's like your eyes times 10,000. That would be the angular resolution for Hubble Space Telescope. It's a good result, but still not good enough to read newspaper from 600 kilometers. Okay, one last problem. We got a yellow light from a helium discharge tube. So we talking electromagnetic radiation once again. Got a certain wavelength, and oh, now it is the diffraction grating. So what's going on with diffraction grating? This is how you produce all of those maxima and minima. This time it's the first order maximum at a certain angle given. So calculate the parameters of the grating. To be more specific, it's the number of lines per centimeter. So it's the number of those slits per 1 centimeter. The condition for maxima, the keyword is maximum. So condition for maxima, d sine theta is m lambda. And if it's the first maximum, then m is 1. And lambda is given. Lambda is 587.5 nanometers. That's your lambda. An angle is also given. So sine of that angle, which once again, the small angle approximation, you can go with tangent or the angle by itself in radians, solving for the unknown parameter, which is the distance between the slits, gives you this much. But this is not the question. The question is for the total number of slits, the number of lines, and the term for the number, it's just the inverse of the distance between the slits. So if the distance between the slits is 2.322 and 10 to the negative fifth meters, then the inverse of that number will produce 431 lines per centimeter. So that would be 431 slits per centimeter. Okay, that's it for this particular chapter. Keep in mind the Rayleigh criterion. Keep in mind the small angle approximation. Keep in mind conditions for minima and maxima. And that's pretty much it for, yeah, this is a pretty tricky problem. You have to keep track of different phase changes and waves traveling through different matter. And remember that every time you travel from a lower index of refraction to a higher index of refraction, there is a phase change. And there's no phase change if you are doing the opposite. Yeah, constructive, destructive interference. So constructive is maxima, destructive is minima. Looking at different interference patterns, you can figure out which one is minimum, which one is maximum. Yeah, you still want to practice all of those problems on your own before you get to all the details and you can absorb all the different scenarios. So it's time to do your homework. That's it for this chapter.